episode, we will discuss binomial probabilities. As the name implies, with bi meaning two, binomial trials have two possible outcomes: yes or no, true or false, win or lose, success or failure, heads or tails. Examples of these include taking a 20-question true-false test, winning or losing 13 games in a football season, or succeeding or failing in a pie eating contest. When the outcomes in an experiment are divided into two categories, the probabilities are called binomial. In these examples, also called Bernoulli trials, after the mathematician James Bernoulli, the probability remains constant throughout all repetitions. A binomial trial is defined by the following conditions. 1. There are a fixed number of observations n. The number of observations is not random, but chosen ahead of time. Number 2. Each observation is independent. This means that one trial does not influence another. 3. Each trial has two possible outcomes, which we will call success and failure. For each trial, the probability of success p remains the same. We will let p be the probability of success on a single trial. Then q is the probability of failure. Just note that while we call p the probability of success, it does not necessarily mean winning. It could be that we define success as whether or not someone has ever seen a UFO, and failure if they have not. Now, if p equals 0.4, then q is 1 minus p, or 0.6. Or if p is 0.1, then q is 0.9. Now, n is the number of trials and x are the number of successes. The formula depends upon how the combinations are written in your book or on your calculator. Let's take a football team that plays 13 games in a season. So n, the number of trials, is 13. We want to find the probability that the football team will win exactly 10 games. This means that the number of successes x is 10. We need one more piece of information, and that is that the probability of winning each game. Let's say that in the last 3 seasons, the team won 24 out of 39 regular season games. So p equals 24 over 39, or 0.62. For the sake of this video, we will round this to 0.6. This means that the team has about 11% chance of winning exactly 10 games out of 13. Now, we can do this using the calculator, but in most statistics books, there is a binomial probability table in which you can look up the answer. According to the Red Cross, the blood type most often requested in hospitals is type O. Also, according to the Red Cross, 7% of the people in the United States have O-negative blood type. However, O-negative blood type donors are universal donors because their blood can be given to people of all blood types. This means that if the patient needs blood, but the blood type is unknown, like for newborns who need blood, O-negative type is used. Let's say we have 10 individuals who can donate blood in an emergency, and we need O-negative blood. We know that the probability P of getting O-negative donor is 0.07. That means that Q is 1 minus P, or 0.93. We want the probability that none of the 10 patients have O-negative blood. P equals the probability of success, a donor with O-negative blood, which is 0.07. Q is the probability of failure, which is 0.93. X is the number of successes, which is 0. And N is the number of blood donors, which is 10. This means that the probability that none of the 10 individuals who have volunteered to donate blood have O-negative is 48.4%. That's really high. If this was your emergency or that of your child, you would want to have more people on hand to donate. On the other hand, if you know that there's a 48.4% chance that no donors have O-negative, then there is a 1 minus 48.4% that there is. Let's see what the probability of either 1 or 2 donors has O-negative blood. This means we have to use the formula twice. We use it once for the probability that only one donor has O negative blood, and then add it to the probability that 2 donors have O negative blood. When you compute this, this means that there's a 48.8% chance that either 1 or 2 donors has O negative blood. One final example. Students often want to know what the chances of getting all the answers right on a true-false test. Let's say we have a 10-question true-false test. First, check to see if we can use a binomial probability distribution. 1. There are a fixed number of observations, n. In our case, n is 10. 2. Each observation is independent. The effect of one true or false answer does not influence the next. 3. Each trial has 2 possible outcomes. There are only 2 possible outcomes, either true or false. 4. For each trial, the probability of success, p, remains the same. The probability of guessing each question right is 0.5, so let's try it. We have the combination of 10 things taken 10 at a time, times the probability of success, which is 0.5, to the number of successes, which is 10, to the number of failures, which is 0. So we have 0.0009766. I am so sorry, y'all. I wish I had better news. You have a 0.1% chance, or approximately 1 in every 1,000 times you will be able to get every question right in a true-false test. In this episode, we discussed binomial probabilities. Try a few. They can actually be fun.